My name is Korey Riskey. I go to Colorado School of Mines. I will be a senior this year. I was working this summer on the characterization of molecular magnets using EPR. These are organic molecular magnets. Most of these compounds are made of tetracyanoethylene with a rare earth metal or transition metal. TCNE is tetracyanoethylene, and the structure is right here. A little bit about magnetism. Our molecular magnets exhibit ferrimagnetism at low temperatures. Compounds can also exhibit molecular magnetic behavior at room temperature, but there are only a couple of known compounds to us. Exhibit up to 32% more magnetism than regular iron, and they can be dissolved in a solvent. They can be placed in a polymer, and it can be made in a flexible substance. Since each molecule is an actual magnet, there's a huge wide spectrum of applications. The most foreseeable application would be high density memory storage for computer systems and whatnot. It's also foreseeable to see it applied in nanotechnology in providing alternating currents for MEMS, micro electronic mechanical devices. So here we're talking about, this is paramagnetism, is where there's no ordering, no specific ordering of your array. In this case, our molecular magnets at higher temperatures exhibit paramagnetism. So this is disorder. At low temperatures, our molecular magnets exhibit ferrimagnetism, which is has a net magnetic moment. For my experiment, I characterized my molecular magnets using ESR, or EPR. EPR is electron paramagnetic resonance, and it measures the energy difference between a spin up state and a spin down state, and uses that energy difference to cause an absorbance. And so when we scan a magnetic field, we have our sample in a magnetic field. So this part of the ESR generates a microwave, which is amplified, and our sample, which is under an external magnetic field, is exposed to this microwave, and then the absorption curve is plotted. The first derivative of the absorption curve is plotted. For our experimental procedure, we have two samples that we were working with. Both of them have manganese in them and TCNE, but one of them has iodine in it. That would be this one. And the other one has cyanide in it, and that would be this one. These two are just different orientations of the molecule. So we ran these two samples with EPR at 10 Kelvin, took it down to helium temperatures, measured it at 10 Kelvin all the way up to 80 Kelvin for this sample, and up to 260 Kelvin for this sample. Yes, in 10 Kelvin increments. For our data, we can see that for this line shape, for our samples, both of them, the intensity increases with lowering temperature. So there's more ordering at lower temperatures. Where it deviates from this exponential behavior is where it's exhibiting ferrimagnetic behavior, which is what is useful to us. And so down here, it exhibits ferrimagnetic behavior all the way down here. You can see that as the temperature, so the temperature is decreasing as we go this way. As we approach 0 Kelvin, we approach ferromagnetism. So that's what we can say about that. My future work will be getting new samples for these because they may have been improperly sealed at the beginning, and we'll get more data for this one and see if we can understand anything more that's going on in here, since we don't have as much data as we do here. So we'd like to do that. We also have another sample, which is iron TCNE, which we'd like to do the same thing with and try to understand what the properties are. What we would really like to know is just what the properties are of these things, how they work, and what their temperatures, the ordering temperatures are, and try to figure out what kind of applications would be plausible for this kind of thing.